Hi, you're either here because you're interested in algorithms and programming, or because you're into friendship bracelets. Now, there's a tiny possibility that you're a fan of both, but regardless, I'll try my best to make it simple enough for both audiences. Feel free to jump around in the video though. Friendship bracelet making has been one of my hobbies for a long time. At some point, I even made one for each day of the week. The community for friendship bracelets is huge, and most bracelet makers would probably recognize Bracelet Book, a place where everyone posts or gets friendship bracelet patterns from. A pattern is basically a grid. The grid is either a grid of diamonds, in which case it would be called a normal pattern, or a grid of squares, in which it is an alpha pattern. Alpha patterns are way more flexible if someone wants to create text or a very specific drawing. And people have gotten really creative with those, while some normal patterns are mainly used for abstract designs because it's difficult to control where threads come and go to have the right colors at the knots where you need them. Currently, how people design normal patterns is they start with certain colors and just knot through until they see something they like. If you have a specific thing in mind, this will be a bit of trial and error. When you look for something that determines the knots for you, you'll only find websites and apps that help you visualize what you're making, but won't make it for you. I wondered if I could create a tool that takes a design you have in mind and just figures out all the knots for you. There's 4 types of knots: forward, backward, forward-backward, and backward-forward. The choice of knot depends on which of the 2 colors you want to appear on the knot and whether you want the thread positions to switch or not. Forward makes the left-hand thread's color dominate, backward makes the right color dominate. Both of these switch the order of the threads going through the knot though. Forward-backward is like forward, but keeps the order of threads the same. Backward-forward is the same as backward, but keeps the order of the threads the same. The first thing I did was create a visualization function, which, when given the initial thread colors and an array of knots, shows me what it looks like. That was important for troubleshooting later. I realized that after staring at printed hex codes for a while. Alright, now the actual algorithm. A few years ago, I saw a YouTube video about how Sudoku solvers are coded as a constraint satisfaction problem, and I wanted to try that. I realized that friendship bracelet solvers could also be seen as a constraint satisfaction problem, but with different constraints. Then, when the constraints don't narrow it down to a single solution, a possibility is picked at random. And if problems are encountered downstream, it backtracks and chooses another possibility. The constraints, or as I call them, rules, were as follows. Rule 1. The number of threads per color must be constant across rows. Rule 2. At least one of the 2 threads entering the knot should have the target color. Rule 3. The threads on the sides that aren't going through a knot should have the same color in the row after. Rule 4. Threads exiting a knot must have the same colors as when entering the knots, regardless of order. And finally, Rule 5. Final threads should have the same order as the initial threads. And that is because the pattern should be repeatable. I used recursion for the purpose of backtracking. So you started a thread between 2 knots, and you're trying to determine what its color should be. So you have a number of possible solutions. You pick one of them and you go with it. You move to another thread while holding your assumption about the first thread. For this thread, you also have a number of possibilities. You choose one and you go with it. Now, if you tried all possibilities with the other threads, but all of them broke rules, you come back to this thread and try another possibility. Whenever all the paths have failed, you backtrack until you have a combination of thread paths that doesn't break any rules and completes the solution. Randomizing the order of possibilities each time helps explore different solutions, which gave me the idea of generating all possible solutions and picking the one with most repetition and most straightforward knots. But that kind of thing took forever for it to finish for medium-sized designs. Time complexity sucked. Surely without it, the time complexity would be good, right? This is the upper bound of the complexity though. Thanks to the rules, the recursion doesn't go too deep because it can tell pretty soon whether that recursion path is a dead end or has a valid solution. Introducing more rules would probably make the average time complexity even better. Finally, I built the graphical user interface. I initially made it so that it only displays the final solution, but I thought it would be cool to show all the steps the algorithm took to get there. And you can even occasionally see it backtracking when it realizes it's made a mistake. I think if I wanted to work on it more, I'd be able to find more rules that would make it even faster on average. Also, I'm not a fan of creating graphical user interfaces with Python, and now that I learned JavaScript and CSS in an unrelated project, I kind of wish I used them for this one. Because if I decided to make it more accessible, it'll be tedious to change all the syntax. To be honest though, I'm not even sure if there's an actual need for this because I think Friendship Bracelet designers enjoy experimenting with the patterns until they get something they like. Still, working on the Friendship Bracelet Solver was fun, and the result was pretty satisfying.